The lesson today is on exponential growth and decay. And just as a reminder, if we have a graph that is a representation of exponential growth, then it tended to look like this, okay? And if it was a graph of exponential decay, then it went in a declining pattern like that. So what we have here in red in the beginning is some information that we actually finished off with yesterday at the end. We had this little formula and we talked about if A was greater than 1, it meant that there was going to be a growth. And that if it was less than 1, it would be a decay. And that the A value represented the initial amount and X was the amount of time. It was right at the end. I think it was the example that talked about the rabbits, I believe. So we're going to start out by writing some, setting up some of these on our own. Something else that I think might be helpful, if you would write down, would be A equals P parentheses 1 plus R over N, close your parentheses, to the NT power. And I'm going to tell you what each of those represents. And I know it looks kind of crazy, but you'll be okay. So A stands for the amount. P stands for the principal. The R stands for the initial rate. The N stands for number of compounds per year. It'll make more sense when we get to some examples. And then the NT power, we already know what N is. T stands for the total years. Okay, so you're just going to want to have that so that as we get to some problems where we may need it, we can go back and look at what each of those represents. Okay, so number 1 says, since 1985, the daily cost of patient care in community hospitals in the U.S. has increased about 8.1% per year. In 1985, such hospital costs were an average of $460 per day. Write, that should say an, equation to model the cost of hospital care. All right, and this right here is kind of the formula we're going to use, which looks very much like this over here. All right, so if we have to write an equation, we're going to start out with y equals. Remember, the A is the initial value. What's the initial amount in this problem? $460 a day. So 460, parentheses, then we're going to put a 1 plus, R stands for the rate. It is 8.1%, but you need to write that as a decimal. Remember, when you go from percent back to just decimal form, you take this decimal and you move it back 2 places to the left. So if we take 8.1 and we move it back 2 places, we end up with 0.081. 0.081. That's an 8, sorry. Close your parentheses. And then to the x power, you're going to put x there. All right, now we're going to simplify this just a little bit. And we're going to write y equals 460, parentheses. We can add 1 plus 0.081 as 1.081. to the x power. That looks a lot nicer to just be able to write it like that. Okay? All right, now it says find the cost per day in the year 2000. Okay? So, first of all, the $460 is for in the year 1985. So from 1985 to 2000, that's a difference of how many years? 15 years. So we're going to write this out again, but in place of the x, which is representing the amount of time, we're going to put 15 because it's going to happen each year for 15 years. So let's go ahead and write y equals 460 parentheses 1.081, close your parentheses, and then to the 15th power. And once you get that, we're going to actually calculate that. So you need to get your calculator out, and you're going to type in 1.081, hit the little y to the x button, type in 15 for your power, hit equals, and then you can multiply by 460, which is out front. Leave it as a decimal because we're talking about money here. Okay, Amber, what'd you get?
1,479.59.
Okay, 1,479.59 something, right? Well, since we're talking about money, we only need two numbers after the decimal point. It was 59 what? 6. So instead of 59 cents, because of the 6, it's going to round up to 60 cents. And then put your little dollar sign there. So that's the answer for that for part B. That's per day. Excuse me, that's the cost per day in that particular year, in the year 2000. All right, now, we're going to find the cost per day. So we're going to start out, I'm going to try to change the color. Start out with y equals 460. There's still the same initial amount. We still have the same rate, 1.081. And it says currently. Well, what's the year currently right now? It's 2016 right now. So take 2016, subtract the original year, which was 1985, and you get 31. So that's what your exponent is going to be. You see how to do that? Because it said currently. Currently, meaning in this year, compared to the original year in the problem. So you should type all that in, and let's see what you come up with. Yes. Okay, so you should be typing in 1.081, then you should be hitting the y to the x power button. That gives you the exponent. Type in 31, hit equals, then multiply by 460. Are you good now? Okay, so what are we getting? 5,123.632, so 63 cents. Very good. That's how much it would cost per day for what? To be in the hospital?
I'm not going to that hospital.
Are you praying?
For these people that have to pay that much money.
It's very expensive. That's why insurance is so beneficial. It's extremely expensive to be in the hospital. That doesn't surprise me. Okay. All right, let's go ahead and look at number 2. Suppose your community has 4,512 students this year. That right there is your initial amount. The student population is growing 2.5% each year. That is your rate. Write an equation to model the student population. Okay, so here we go. They all start out the same. Y equals, what's the initial amount? Good. Okay, times. Now, it's usually 1 plus, but I think we could probably go ahead and skip that middle step. 1 plus, what's 2.5% as a decimal? 0.025. So we're just going to write 1.025, right? Okay, to the x power, because it doesn't say for how long. That's just our equation that we could use. And from there, we can figure it out for any amount of time. Part B says, what will the student population be in 3 years? Okay, so the time is 3 years. So we're going to write y equals 4,512 parentheses 1.025 to the what? Third power for 3 years. Nicholas?
4,858.
Yep. Very good. That would be the student population in 3 years if the community continues to grow at this rate of 2.5% per year. Okay? All right, number 3. Number 3 says, suppose your parents deposited $1,500 in an account paying 6.5% interest compounded annually when you were born. Write an equation to model the balance. All right, so we start out with y equals 1,500. Okay, 1.065 to the x power. That's our equation. All right, then find the account balance after 18 years. So here we go. Y equals 1,500 times 1.6065, sorry, parentheses, to the 18th power. Okay, who's got that? Michael.
4,659.98.
Very good. $4,659.98. And don't forget to put your dollar sign. Great. This isn't so bad, right? Okay, good. All right, let's go. So far, what else is she going to throw our way? We don't know. Surprise, surprise. Could it be this easy? Number 4, suppose the account in example 3 paid interest compounded quarterly instead of annually. Okay, let's stop for a minute. Quarterly. That means if you take a year and you split it into quarters, which means every 3 months, right? Every 3 months into quarters. 3, 3, 3, and 3. Okay, so what it means is if you were to figure out the interest just for every 3 months, get that percentage rate instead of for the whole year. All right, so we're going to start out with y equals, we're still going to have our 1,500. What's going to go in our parenthesis? Okay, hold on a minute. 1 plus, because this is where it's a little different because of the rate. The rate's a little different. It was 0.065, but that was for the whole year. Now we're going to do this quarterly, which means 4 times. So you need to write 0.065 divided by 4. Because it's going to happen quarterly, meaning 4 times a year. So, oh, I think I said that wrong. It's still the 6.5% for the year, but they're just, if you divide it by 4, that tells you what percentage it's going to be figured every 3 months. Okay? All right. And then we're going to close our parenthesis, and now our time, it says quarterly instead of annually, find the account balance after 18 years. Okay, now for the time, are we still going to put 18? Is it only going to be compounded 18 for 18 years, 18 times? No. What do we need to do to figure out how many times that's going to be calculated? How many times a year does it happen? 4 times a year for 18 years. So what are you going to put? 18 times 4. Put that, you can just kind of put that in parentheses there. And then, yes, we'll rewrite it with the 72 out there. Actually, you know what? At this point, it might be better. It might be easier on you if you go ahead and figure out what 0.065 divided by 4 is and then add 1 to it so that you can just put that in here. Nicholas, what did you get?
0.01625.
Okay, and then put the 1 in front. And then you guys said to the 72nd power. So in order to get that number in parentheses, we just did 0.065 divided by 4. That came out to 0.01625, and we added the 1, 1.01625. to the 72nd power. All right, and then we're going to calculate that. So you know how to plug that in, so go ahead and do that. This is as hard as it gets, really, is when you have to think about it happening quarterly or semi-annually. All right, Hannah?
I got 4787.75.
$4,787.75 is correct. Okay, so that was a little bit different, but I think you see why. Okay, if it's going to happen quarterly, that's going to change the rate, and it's going to change your years. Okay, let's look at number 5. We're not going to use that chart there. Find the account balance after 18 years compounded monthly. Okay, so we're still using the y equals 1,500. We're still going to have the 1 plus. It's still 0.065 divided by 12 because it's monthly. And then it's 18 years, but it's multiplied by 12 because it's happening 12 times a year. So let's simplify this a little bit. So do your 0.065 divide by 12 and add 1 to it. And tell me what you get. Hannah?
1.0054166667.
Okay. And the only reason it probably has that 7 on the end is because it can't put any more 6s in your calculator. All right, and then 18 times 12 would be 216. I would say after you've written it out that many digits, you're probably going to get a fairly accurate answer. I wouldn't just write 1.0 and stop. I'd go out as many digits as you can. That'll help you get close. Because after all, your answer in terms of money is only going to go out 2 digits, right? For cents. Okay, so when you calculate all of that together, anybody different have an answer? I keep calling on the same people. Nicholas?
On my calculator for like when you got the 1.0 by 4 and 6.667, I only got 3 sixes.
Yeah, you added an extra 6.
Oh, probably. But yours would have kept saying 66666 if there was more room. So I don't think it really matters. All right, Samira.
4,817.75.
$4,817.75. Yes, very good. Okay, just got 2 more. Y'all doing okay? Okay, number 6. Number 6 says, since 1980, the number of gallons of whole milk each person in the U.S. drinks each year has decreased. How many of you like milk? Raise your hand if you like to drink milk.
I like chocolate.
Okay, well that's okay. Yeah, good. Okay. All right. So whole milk though is really thick milk. That's usually that's what Finn has to drink. Babies have to usually drink that till they get enough meat on their bones, and then they wean them down to 2% and 1%. And then if you're like me, I just drink fat-free milk. I'm used to it, so hey, but with some Oreos, it tastes pretty good. So if you go fat-free on the milk, you can eat the Oreos. It kind of all works out, right? I love that all this is on YouTube right now. Like, that's a crazy teacher. Okay. All right. So 4.1%, it decreased. Circle that. That's going to be really important when we go to set up our equation. Okay. In 1980, each person drank an average of 16.5 gallons of whole milk per year. Write an equation to model the gallons of whole milk that's drunk per person. Okay, what is different about this formula versus the one we were using before, and why? Nicholas?
You do, like when you get the 1, you get the 1 minus.
It's got a 1 minus instead of 1 plus because?
Because the rate is decreasing.
Good, the rate is decreasing. Very good. Instead of increasing. And so you won't normally be given that. You've got to take note whether the problem is talking about an increase and you use the plus, or a decrease and you use the minus. So you have to pay attention to that. Okay? All right, so here we go. Y equals, what's the initial amount? 16.5 gallons. Okay, 1 minus, what's the rate as a decimal? 0.041. Close the parenthesis to the x power, right?
Yes.
Okay, now let's actually calculate that. It says use your equation to find the approximate consumption per person of whole milk in 2000. Okay, so you got to go back and see what year they were initially taking this data from 1980 to 2000. So that's going to make our x be what? 20. Okay, so we have y equals 16.5 parentheses 1 minus 0.041, or if you already calculated that, to the 20th power. So you could, in your calculator, just do 1 minus 0.041, hit equals, then y to the x, take that to the 20th power, hit equals, and then multiply by the 16.5. Cece, what'd you get?
I got 7. Do you want me to use all the numbers?
No, go to the hundreds place.
7.14.
7.14, and what are we talking about? Gallons. Gallons of milk. So, because it's decreasing, that is approximately how many gallons of milk each person will drink in the U.S. by the year 2000, which if it's going to continue at that rate, it's going to go lower, won't it? So it just kind of depends. Milk also went up in cost there for a while. Of course, it was after that, I believe, and after 2000, because now we're in 2016. That's just crazy. I graduated in 2000 from high school. That means I'm old. That's what that means. Okay, and by the way, when you asked what number to go to, and I said the hundreds place, unless it's set in the directions what to round to, then technically you could choose. There's not really a right way or a wrong way. I'd say you're pretty safe to always go out to the hundreds place. I wouldn't write 7. Unless it said, oh, and it does. Approximate, you might could put 7. But 7.14 is good too. That's an approximate. That's not an exact because it kept going in the calculator, right? The number did. And so we approximated it by rounding it to the hundreds place. I realize that I talk very fast when I listen to myself on these videos. If y'all ever need me to slow down, you just got to speak up. Okay, number 7. In 1990, the population of Washington, D.C. was about 604,000 people. Since the population has decreased about 1.8% per year, or since then, it has decreased 1.8% per year. Write an equation to model the population of Washington, D.C. since 1990. Okay, so here we go. Y equals what? 604,000, parentheses, 1 minus 0.018, close the parenthesis to the x power, right? Because once we write the formula or the equation, then we could calculate this for any number of years or any amount of time, right? By having the x there, because you can plug anything in for x. Okay, then part B says, suppose the current trend in population decay continues. Predict the population of Washington, D.C. in 2010. Okay, well, we don't really have to predict it, being that that's already passed now, right? Maybe this was an old problem. But we can still go ahead and calculate it. So it went from 1990 to 2010. So, oh no, my iPad just died.
Oh.
I wonder, I don't think I can write on it. Okay, so I'm just going to finish talking this problem out. Okay, so I was writing y equals 604,000, parentheses, 1 minus 0.018, close the parentheses to the 20th power, and then you were going to plug that in, and when you plugged it in, you should have gotten, check me on this, 420,016.83. That would be 420,016.83. Yes? Okay, awesome. Well, that's the end. This is 9-2.
I think it was on the last one.
I know.